Hi, everybody. Welcome to my presentation. I'm Mariana Oliveira, Marie Curie PhD student at Partenope University of Naples at ReTraCE project, funded by European Union's Horizon 2020 Research and Innovation Program. I'll be online to answer your questions and talk to you on May 4th during my session from 3 to 3:40 p.m. UTC time. Let me start the presentation about the integrated LCA and energy accounting sequential evaluation. It's well known that the current production economic model causes increasing in pollution levels, resource consumption in exponential growth scale, and consequently its depletion, and also species losses and ecosystems degradation. When I was preparing this to you, my research group shared this interesting paper, which points out evidences between economic growth and biodiversity conservation, arguing that there is a conflict between them. However, our future seems to be keep growing. Accordingly to the European Unions, we will be 68% human living people by 2050, concentrated in mega cities. Currently, they are 33, but by 2030, it will be 43. We will need infrastructure. We will need food, energy, water, resources to support our way of living. Those resources are generated far from the city centers, and the effects of urbanization affect areas also beyond the city's boundaries. Urban systems are complex. We need a microscope to be able to overcome this complexity. To manage a process, we need information, indicators, and the simultaneous application of different evaluation methods gives us management information, gives us a systematic understanding of process from different perspectives, scales, and points of view. So, LEAF is the procedure based on the sequential application of LCA and energy accounting methods. The first step includes the implementation of a preliminary LCA to provide a picture of the state of the system and identify the hotspots. The next step is the scenarios choice, based on specific improvement steps and then evaluated by means of energy accounting to assess the demand for biosphere resources, support, and the environmental performances of the proposed solution. At this point, several hypotheses can be put forward by assuming different technological patterns capable to remove the identified hotspot at the previous step. Each scenario provides different energy-based performance in terms of resource amounts and quality, showing different sustainability perspectives at the scale of biosphere. The final step is the exposed LCA to test each scenario results in terms of decreased impacts in order to assess if the hotspots and the related environmental costs have been actually removed. LCA stems from the basic principle that in order to accurately assess the environmental impact of a system or product, all its productive stages must be included in the analysis, from cradle to grave. Several impacts are evaluated and indicators developed in order to provide a clear picture of resource use and environmental damage generated within a process or economy. LCA provides information about the resource and environmental cost of a given product or process, accounting for matter and energy flows occurring under human control. On the other hand, energy accounting looks at the environmental performance of the system on the global scale, taking into account all the free environmental inputs, as well as the indirect environmental support embodied in human labors and services. EMA is a powerful thermodynamics-based and systems-oriented method which provides evaluation of process from an environmental perspective. Energy is defined as all available energy directly and indirectly used to produce a resource in the biosphere, as well as to generate a product or a system in the economy. This is exergy concept. And it uses solar energy as common denominator to express all flows in a common unit, since it is the basis of the development of every system in the biosphere. To calculate energy value of a resource, it's necessary to know all the thermodynamic work required to produce it over time. LCA, for example, begins from cradle mining, while EMA starts from the resource generation within environmental domains. Fossil fuels are evaluated on EMA, starting from phytoplankton sequestration over hundreds of millions of years. Instead, fossil fuels are evaluated in LCA, starting from its extraction. Those methods complement each other, as you can see on this inventory. EMA inputs, signalized in orange or yellow, consider the same information of LCA in blue. But also EMA includes on the top renewable and non-renewable natural resources, and also labor and services at the bottom part. I will present to you results of LIFA application on another European Union's funded project, EUPHORIA. This study was in Italy, Campania region, Naples City. The goal was evaluating alternatives towards a sustainable urban system, in this case, energy efficiency. Functional unit is 1 square meter of Naples areas in one determined year. This simplified energy system diagrams of Naples shows the boundaries and the interconnections between the different levels within the city. The inputs are represented by the letters. So, R for renewables and specifically R1 for additional energy required to dilute the downstream environmental impacts of the city. N for non-renewables, F group here is the representation of LCA inputs. They are imported energy, food, water, and other goods. You can see also labor and services, here divided in renewable and non-renewable fractions, and also W for downstreams environmental impacts, emissions absorbed by the environment. So, the first step is the ex-ante LCA of Naples urban system. Characterization graph shows the relative contribution of the main input flows to the total burden of the urban system. The main contributors are electricity, 25%, followed by metals, electronics, and fuels input flows. Electricity is the hotspot that will be evaluated by EMA scenarios. The first scenario here is the improved business as usual with statistical variation of electricity inputted flow in order to explore sensitivity to data errors, uncertainty, and unavailability. On the left of your screen, you find the energy value graph without labor and services, and on the right, considering labor and services input values. Results do not show significant deviation in terms of energy indicators from the mean value calculated without any assumed variation. When it includes labor and services, higher energy value on the right, it's possible to evaluate the resources cost of know-how, information, and infrastructures on local scale. Instead, when energy does not account for labor and services, it helps to understand the process on larger basis. Our second scenario is the technology-based efficient improvement. It evaluates the reduction of electricity input flow through the substitution of traditional lamps for LED ones. The comparison of energy value between these scenarios to the first one, business as usual, does not show significant improvement due to the relevant weight of labors and services energy flows and the limited improvements of the selected hotspots. Only LED lamps as technological improvement doesn't seem to be the answer. Our third scenario is eco-efficiency implementation, considered substitution of conventional electricity mix with a share coming from photovoltaic and wind. Again, comparing to the first scenario, business as usual, the reduction of energy value without labors and services on left, it's equal to 16%, showing that this option is an overview of how it's possible to achieve more environmental sustainability in the investigated system. This is caused by the use of the unit energy values to convert inflows to energy values. Do you remember? Solar energy is used as common denominator to express all flows in a common unit. So UEV is the solar energy required to generate 1 unit of output. As photovoltaic and wind are more eco-friendly secondary sources, their UEVs have a lower value compared to the UEV value of the Italian electricity mix based on burned natural gas and hydroelectricity. At this point, an ex-post LCA evaluation for each scenario should confirm if expected decrease of the environmental burdens were actually achieved. In conclusion, LEAF, LCA and energy accounting integrated procedure is developed through the sequential application of both methods, providing a multi-criteria analysis through 1, the creation of different optimized scenarios, and 2, the identification of hotspots, the most significant contributors. LEAF provides insights from the donor side, energy, and from the consumer side, LCA, allowing a better and deeper understanding of the different investigated options and their feasibility, performances, and burdens. Moreover, LEAF allows to investigate several options from different points of view with different approaches, revealing strengths and weakness of each design scenario. Concisely, LEAF indicators successfully highlight the hotspots, making possible the exploration of a whole set of results, reporting both the upstream environmental support to the analyzed process and the downstream impacts, the emissions loading on the environment. This enables a more realistic and multi-criteria approach to decision making and environmental management. So, thank you so much for your attention and keep in touch.